Hello, everyone. Can someone use the chat to let me know if you guys hear me? Okay, great. Let me go ahead and get started. So I'm going to start with some announcements. You probably have finished quiz 1. And next quiz will be published like this one next Monday. Yeah, I mentioned that we're gonna have one quiz per week, except some weeks maybe we don't. The second announcement is about the lab project that is due at 8:30 today. So in addition to submitting your report and your code, you are supposed to also submit a peer review. So this is the form that will be today uploaded on Learn. So this is a rubric for peer review. There are certain items that we put here: cooperation, for instance, team role fulfillment, ability to communicate, quality of work, meetings and response time, time management, and overall contributions. So the way it works is that you have the criteria here from 1 to 10. So read the criteria, read the description, and based on that and your judgment, give yourself. So here comes you. You're going to put your ID and then your name, and then how you rate yourself, and then how you rate your teammates. So for a group of 4, we're going to have 4 names here, and then 4 numbers from 0 to 10. What is important to us and for your grade is the last one, which is the overall contribution. So the number that comes here is the most important one, and it is the one that we'll use to calculate your grade. So this is the one that is important. The rest of them are just here to give feedback to yourself and to your teammates. Excuse me. We also provide some space here if you want to give your teammates some comments, things that you think that they should improve, or things that you really like about how they have contributed and how they worked within the group. So I would recommend doing this. After you submit this, we run a script. We will run a script that will summarize all of this, and then we'll send anonymous feedback to all the members. So your teammates wouldn't know how any particular groupmate has evaluated them. They just get anonymous, like member 1, member 2, member 3 in your group evaluated you this way. So they're going to see all these numbers that you provide, all these grades, and if there is any comments. Yeah, so So please make sure that you also submit this form. Again, it will be uploaded on Learn, and I believe more details to come, but I think we're going to create a Dropbox for each one of you where you can actually upload this. Okay. Then we're going to go to the slides. Okay. Oh, I got a couple of questions. So when do we need to submit the form by? So it's going to be due on exact same time. No, actually, let's. Yeah, we haven't thought about it. Probably within an hour after your submission, it should be about an. I mean, either with your submission or about an hour after your submission. Please submit this form. More details to come. So, with exact instructions will be emailed to the class. Is a separate kernel stack created for each thread that is created? I will definitely talk about that. And it would need to be individual Dropbox, right? Since the group Dropbox is shared. Yes, so we'll create individual Dropboxes. Okay, so let's. I'm gonna just summarize what we're up to, and then start getting into the details of where we left off from last lecture. So we are talking about implementing threads in a multi-threaded kernel. We said, so this is the figure I want everybody to remember. This one, oops. Yeah, this one is the one that I want everyone to remember. And this is actually what you're gonna implement in your lab. So lab 2 is about creating threads and managing threads. There in the lab manual, we call them tasks, but the idea is the same. So we're gonna have kernel threads. So each one of these kernel threads are going to do kernel-related tasks and stuff. So each one of them only has a kernel stack, a TCB, and it's running. We also will have user space processes and user space threads. So each one of those will have a stack of its own inside the user space. And then the kernel creates a stack or allocates a stack for that thread inside its own memory. So this second kernel, a second stack, will be used for kernel-related jobs and routines. That's why we have it separately. And we talked about why we can't actually use this stack when an interrupt happens or when we want to take care of system calls. So we're going to use this as stack. So we will talk about that. So I got 2 questions. So does each TCB have a distinct kernel stack pointer? Yes. So this is an implementation decision that you have to make in almost all modern mainstream kernels that I know. You have a separate kernel stack per TCB. Now, in the past, where memory was actually very expensive and very limited, you had versions of, for instance, Unix, where you actually didn't have one separate kernel stack per thread. You only had one kernel stack that No, even those, they didn't have one, but a bunch of them, but they didn't have a separate kernel stack. But the one that we're talking about and the one that you will implement in your project, you're going to have one kernel stack per task, per TCB. When can we see our quiz grades? Soon. Okay. Okay. So we talked about this function. How much memory is usually reserved by the kernel? So I got a question. How much memory is usually reserved by the kernel in modern OS? If you're asking about kernel stack, it would depend. I think in your book it mentions 8 kilobyte. In our project, because we don't have much memory, we're going to use like 0.5 kilobyte. Other than that, the virtual memory of kernel is as big as virtual memory of everybody else. But then, depending on how much memory you have, you want to load the portion of your virtual memory that is being used. So that's another discussion that we will have later on. Let me get rid of my own video. Okay. Okay, so this was an important thing that we mentioned here in thread switch. When we talk about return, where do we return really? Well, we return to whatever address that we have on the stack. And we get into thread switch as old TCB, and we get out of it as new TCB. So at this point where you change the stack pointer, so here stack pointer, your processor's stack pointer is going to point to the kernel stack of this new TCB. So here this pop AD and then return are going to use this kernel stack. So they're going to assume that there has been a push AD executed. So this pop AD will work. It will just pop whatever push AD pushed in the past. It also assumes that you have a return address that it has to use to return. Every time you call this thread switch, you have to be sure that the kernel stack is prepared for these two instructions to come, because these two instructions are always here after you switch to this new TCB stack. I've got two more questions. Like the kernel's memory region in total, how much memory overhead it represents, or does it allocate memory to itself dynamically? I think you're asking about a physical memory, if I'm not mistaken. If you're asking about virtual memory, right before, I actually prefer to answer this question later on when we talk about virtual and physical memory in detail. So keep that question if you don't get an answer later on when we start talking about memory management, definitely bring it up. So I'm going to just postpone that question because it requires some explanations. Okay, anytime you write to virtual memory, are you making a system call? No, not really. So every time you execute, load, or store, you're writing and reading from your virtual memory. So not really, you're not calling any system call with that. Where is SP being initialized? That's a good question. Next slide explains that. So here I'm just reviewing what we had in the previous lecture. Here is where we initialize the stack. When we create a new thread, let me load all the content and then talk about it. Okay, so few things here to note is this is where, oh, sorry, the code is actually in the previous slide, not next. So it's, go and look at create thread. That's where we created a stack, kernel stack for each thread that was created. I got another question. So aren't you accessing hardware? Oh, okay. So how do I publish this? Oh, it's private. Okay, so somebody is confused about hardware. So if you go back to the slides that we have where we drew the line, protection line, there are things that we have to provide to the application. The registers, for instance, inside the processor. This is hardware, but we're allowing the user to use them. When you do, add two registers and then store the result in another register, that you're accessing hardware. The same way with memory. It's okay to let the software use memory. What is important is to not let them access somebody else's memory or the operating system's memory. That's where the protection comes, and we'll talk about that later. I mean, we mentioned about memory mapping, where you map from virtual memory to physical memory, but we'll talk in details what that means. Okay. So talking about this code here, this is how we yield. When a thread yields, we trap to OS, we start running the system call, kernel yield, and then this system call is going to call run new thread, and then run new thread is going to call thread switch. So the job of this run new thread is to get the thread off of the execution mode and make it ready. So the state of the running TCB becomes ready, and then this thread is going to be added to the ready queue, and then we're going to execute the thread switch. The code after this, in the context of this running thread, won't be executed, because the moment we go inside thread switch, we're going to start executing this chosen TCB's context. But at some point, we're going to be scheduled again. This TCB is going to be picked up, and somebody else is going to run thread switch, and as an argument to that is going to choose this particular TCB that just got yielded the CPU. At that point, what will happen is that inside thread switch, we will pop the registers that we push before context switching, and then we will return. And then when we return, we start executing from this line. And once this is done, so here, after this function is done, we're going to return again. We'll return to this kernel yield, and then kernel yield is going to return to this thread yield, which has been gone. So we're going to just actually return to compute pi. So let's look at that in an example. Let's say we have two threads that are running these lines of code. I got another question. In create new thread, it only creates one stack, but there is a kernel stack as well as a thread stack per thread. Which one gets created and where is the other stack? That's a very good question. So to answer that question, the one that we create in create new thread is the kernel stack. So in the slides, we're assuming that the user library and user program will first create its own stack inside its own library, and then call the system call to create a thread. So we're assuming that the kernel thread has been created. The user spaces stack has been created, and now we're just creating the kernel stack. In your project, because we don't have a user library, you will have to create both of the stacks yourself. Although one of them is a static, we already have it, so you just set a pointer. The other one you will create yourself. That was a good question. Okay, another question. What does compute_pi do? Compute_pi, if you go back to the slides, it's just a function we were talking. It was an example. So we had a function that would compute pi, the number, the value of pi, and it would just compute a digit and then yield, and so on and so forth. In thread switch, when we cache old threads SP, is that the kernel SP or the user SP? Everything here is kernel. We're talking about implementation of kernel. So everything here we're talking about kernel, unless it's specified. Okay, now let's look at this example. Let's say we have two threads running this code. If you look at the code, it has two functions, A and B. A calls B, and then B has a while loop that would just yield. So it wouldn't do anything, it would just yield. So this is the initial setup. Let's say they're executing. So they have been created. I'm not going to talk about the creation of them. So let's say they both have been created. Now let's say we start with thread A. So thread A runs A. So this is the stack of thread A. We put A. Then A is going to call B. So we put the frame for B. Then B is going to call thread yield. And then thread yield is going to call into kernel. So we're going to put the kernel yield here. Then kernel yield is going to call run new thread. And run new thread is going to call thread switch. At this point, we're going to switch to thread 2. So we're going to stop here. So everything will look like this. So the user stack will be like this, and the kernel stack for thread 1 will look like this. And then we're pausing here. We're not going to do anything else with thread 1. We'll start with thread 2. Now stop is going to call A. A is going to call B. B is going to call thread yield, kernel yield, run new thread. And at this point, run new thread will call thread switch. Now we switch back to thread 1. Now we continue from where we left off in thread switch. If you look at the thread switch code here, we're going to execute the pop AD. So we're going to pop everything we pushed previously, and then we're going to return. So after we return, where do we return? We return to run new thread. This guy also returns. Then this guy returns. We're back to thread yield and then B. Now we start executing B. Again, it's going to call thread yield. The same story again. We're going to switch. The same story, as you can see. Hopefully that was clear. Now, a few details about switch. It's something that many people consider a very hard to code. It could be frustrating to implement this. We're going to give you the implementation of thread switch, although you will have to make some changes. but generally speaking, you have to make sure that you save and restore all the registers that are available. Let's say 32 registers you have. In our case, it's much less. In our boards, you have less registers to save. But if you actually make a mistake and don't save the registers that you have to save, you may or may not face a problem. Let's say there was one register that you forgot, but then this register most of the time no thread uses, or maybe the compiler never uses that thread, maybe. So you're going to be fine. But then you start running a code that uses that register and you haven't saved it, then you start seeing a lot of errors in your code. So it's really important that this is implemented diligently. Testing of kernel code is possible, but very expensive. That's why almost nobody does test like a formal test of kernel to prove that it works the way it has to work. That would require exponentially large memory space. So anyways, now, if you remember when we were talking about thread create, we talked about this dummy switch frame that I said I'll talk about it later. So here is where we want to talk about it. So if you remember when we were creating a thread, we pushed a bunch of stuff, and then right before we return from the function, we pushed a dummy switch frame. Let's see why that is needed. So look at this code. This is the code of thread switch. Push ID, saving the stack pointer, bringing or switching the stack pointer to the new thread, executing pop ID, and returning. So whenever a thread switch is called, it assumes that these two should be executed on the new TCB. Now, if it is an old TCB that was running already, then you have this pop ID already on your kernel stack because you have previously executed this push ID. But if it is a new thread, you never ever previously called thread switch on this newly created thread. Therefore, the stack doesn't have this the registers that push ID pushes. That's why we have to actually push these. Now, what should we push? It really doesn't matter because generally speaking, this push ID is going to push all the general purpose registers. We really haven't started executing this new TCB, so whatever you push for those registers, it doesn't really matter. You could just push nothing. So here we're just superficially by manipulating the stack pointer with the size of pop ID, what we're doing here is basically pushing nothing to the stack. And then we also have the return address to the beginning of a stop here. One particular thing to mention here for your project, things work a little bit differently than what I'm explaining here, because this portion where you put the stop function as a return to the beginning of stop is a little bit compiler dependent. So in order for us to avoid messing up with this, we're going to inside switch do two different things. So instead of having one thing that works for new threads and old threads, we're going to separate it. Say if it is a new thread, do these, and if it is an old thread, do other stuff. So if it is an old thread, do exactly like this. But if it is a new thread, do some other stuff. You'll see those when you start working on lab 2. I got another question. What is it again that is pop pop in pop-AD in thread switch in terms of the data? Is it pushing the top of the kernel stack for the other TCB? A bit confused here. So, okay. So what is push AD and what is pop AD? Push AD is just one instruction, but what it does, it actually pushes all the general purpose registers that you have. It pushes all of them to the stack. Now, what is stack? Well, whatever stack pointer is pointing to, which at this point, when you execute push AD, the stack pointer is pointing to old TCB's kernel stack. So we're pushing all the registers to the kernel stack of old TCB. Now, here we change the stack pointer to point to new TCB's kernel stack, and then executing pop-AD. Pop-AD reads all those registers. So the same set of registers that are pushed here are getting popped. Again, these are instructions, I think, for x86. For other architectures, you might have specific instructions, or if you don't, then you have to one by one push all the registers that you have to push. Okay, so then I got another question. What is the stop here? Go back and read the slides, please. I got another one. Shouldn't return from thread switch return to after the thread switch invocation in run new thread? No. Shouldn't return from thread switch return. Yes, it should actually, and it does. So whenever you call switch here, after you execute these two, when you return here, this return will return, in the case that this is a thread that was running before, you will return to the line after thread switch inside run new thread. So your question was correct. I don't know. I answered it. So the purpose of push AD is to push the state of the thread before it yields. Yes. Okay. Now, what happens when threads, yeah, there is a mistake here. Let me just fix it right away. When threads block on I/O. Okay. So what happens when threads block on I/O? Let's look at it. Let's say that we have a thread that is copying a file. So when you call copy file, inside that you're going to call a read, hopefully, and then this read is going to trap to the OS and call a system call, kernel read, and then this will initiate the read. If you remember the top and the bottom halves of the driver, so this guy is potentially calling the driver and doing stuff. So it does that. It does initiate the process, but hopefully we don't want to wait here and do nothing. We want to start running someone else. So at this point, you call actually run new thread. So after you initiate the process, you call run new thread. The only difference here is that we don't put this thread to the ready list. We put this thread to the waiting list, so that when the data, when the data comes and the I/O interrupts us, that the data is ready, we'll pick this guy up and then we'll start running from where we left off. So this run new thread is going to call thread switch, and we're going to switch to someone else that is ready. We're not going to waste cycle here. And then whenever the data is ready, we'll just pop everything off of the kernel stack and go back to executing the thread. We got a question. I know that we have a stub in the kernel stack, but what's its purpose? Why is it Okay, so the stub is not necessary and you actually don't have it in your lab project. It's just we put it there as a level of indirection to get some information to, you know, do some stuff before executing the thread. You could potentially do all of those inside thread create. So it's not necessary. It's just one level of indirection. We talked about the fact that you can actually call thread exit in case that your thread doesn't call thread exit. So there are a bunch of housekeepings that you can do inside stub. I got another question. So in the case of a new thread, the return address pushed onto the stack in push dummy frame would point to the instruction after thread switch is called in this what? So push dummy switch frame would point to the instruction after thread switch is called in the stub. So the way that your slides are, basically we push before we push the dummy stuff. We first push the address of a stub, and then we push the dummy stuff like nothing. And then inside the thread switch, you first execute pop-AD that would pop all the nonsense, and then it would execute return. At this point, the return will go to the beginning of a stub because that's the address we pushed on the stack. So it uses that address to start executing. Okay. Next is involuntary context switch. What happens if thread never calls IO or never waits or never yields? Well, you can't really trust the thread to be a good citizen and yield the processor. That's too much to ask. So let's say you have a thread that computes pi all the time and it never yields. So you don't want to all the time execute that guy. At some point, you're going to start realizing that you have to interrupt your threads. I got another question. So in our lab project, isn't the SVC decoder we use the stub? So the SVC in your lab project is kind of like the system call handler. So whenever this is a system call handler, if you wish, that would be called first. Okay, you guys are asking a lot of questions. Okay, so where are we? OS utilizes external events. In the context of operating system, we are actually talking about a timer. So every time we context switch to a thread, usually the kernel sets a timer, and then this timer will expire, and when it expires, it raises it traps to the kernel, and then the kernel decides whether or not to run the thread that was running or run some other thread. One thing here to note, which is very, very, very important, interrupt handler is not a thread. I repeat, interrupt handler is not a thread. Why? Because it's not schedulable. The kernel scheduler does not decide when to run interrupt handler. Interrupt handler is immediately executed when an interrupt happens. So the moment an interrupt happens, the hardware is going to go inside the interrupt handler table that we talked, and is going to find the function that is associated to the interrupt that happened to run. So there is no scheduling going on from the kernel side. If you wish, you can think of it as a routine call, but it's not a thread. So one thing though about it, it could initiate threads. So inside interrupt handler, you can create a thread, you can call a thread, you can send a signal to a thread. So it can actually work with threads, but it by itself is not a thread. And it would always start immediately after an interrupt happens. An aside here, how do we track the running TCB? So this is a question to think about. How do we know which TCB we're running? This question is not a hard question if you're running in a uniprocessor, because on a uniprocessor, inside your kernel code, you could have just one variable that would always point to the running thread, which is actually the case in your lab. So you have only one variable that always points to the running thread. And you can just switch that variable every time you do a context switching, and it's always there. But what happens in a multiprocessor? What if you have multiple processes? Can you still have a variable that you use? Well, it's a little bit tricky. Why? Because all the threads, all the kernel threads, use the same code. So if you only have one variable that is going to point to the running TCB, well, you have let's say four processors, and the scheduler might run the code of the scheduler might run on each one of those processors, and is going to attempt to change that variable, and then you don't know which one of these running TCBs that variable is pointing to. Now there are solutions to this. You can use your compiler. So the compiler could dedicate a specific register on each processor to point to the TCB that they're running. So we will just dedicate this task to the compiler to take care of. The other solution is for the hardware to provide a dedicated register for us. So that's another solution that then the OS can use. And the third solution, if you don't want to trust the compiler, or if you don't want to use or if your hardware is not providing a specific register, then there are possibilities here. We can do a software solution where what we do is that because we have fixed size stacks, like kernel stacks usually have a fixed size, if they're aligned, right, we can put the running TCB at the end of or at the bottom of the stack. So at any given time, you know the stack of the kernel stack of your TCB. You just go to the bottom of it. Again, if they're aligned and if they have a fixed size, then you can basically point to that and then find the running TCB over there. So this is an aside that is important. Okay. So what time is it? Okay, back to the lecture. So back to the problem that we mentioned about if you don't have basically a good behaving thread that yields the processor. We talked about the solution that would be the timer interrupt that would expire, and then the scheduler will decide what to run. Let's see an example of this. So you were running your routine, then interrupt happens. So what you do is that you come to the kernel stack after the interrupt happens. The kernel space. You use the same kernel stack to basically deal with this interrupt. And let's say you decide to run another thread. So at this time, you execute the run new thread, and then you switch. OK, so now a little bit of discussion here. There are many threads in modern processes. So this is like this. I took this a snapshot last year. If you look at this, Dropbox in my system at the time had 142 threads. Firefox had 69 threads. So these are big numbers, right? In total, in my system at the time, I had more than 2,000 threads. When at the same time, I only had 400 processes. So a lot more, like 5 times more threads than processes. Now, why these numbers are important? Well, from the OS point of view, the frequency of performing context switches is about 10 to 100 milliseconds. Usually in modern operating systems, you context switch within that frequency. The context switch time in Linux on this Intel i7 and Xeon processors was about 3 to 4 microseconds. I got a question. I'm a bit confused as to how the interrupt signal is generated. Is it like a separate chip aside from the CPU that would generate the interrupt? So I would refer you to the slides that we had, the concepts, the 4 concepts when we talked about interrupts. I have a figure there with the interrupt controller. So all the devices that are connected to the CPU, they can actually raise an interrupt. They can put an interrupt signal, and then the interrupt controller is basically constantly checking all those lines. And if somebody is raising an interrupt, it would detect and it would raise a bit to the processor, and then the processor would notice that there is an interrupt happening. And then based on what it is, it just goes and traverses the interrupt table to find the interrupt handler associated to that interrupt. Now, when we're talking about the timer, so the timer is basically a hardware inside your processor chip that would the operating system can set it, and then when it expires, it raises the interrupt bit. The processor will notice it, and then it's as if the interrupt has been raised. I got a question, just confirming, context switch means switching processes. Context switch means switching depending on the context. If you have a multi-threaded kernel, context switching means context switching between threads. You're running one thread, now you're running another thread. Now, this could potentially mean context switching between processes as well, if these 2 threads that you're context switching between are from different processes. So if you're talking about a multi-threaded kernel, you're context switching between threads. If you're talking about a uni-thread processes, then you're always context switching between processes. So if your processes, each one of them only has 1 thread, then you're basically context switching between processes. Now, these numbers are important because the context switching time is basically an overhead, and the overhead should be really lower than the frequency or the interval of context switching. One thing here to note is that thread switching is always faster than process switching. So when you're context switching between threads within a process, it's always faster, and it's about like 100 nanoseconds. So this microsecond here is when you're switching between threads of two different processes. If you switch across cores, this is called migration. So if you're migrating a task from another process, that would usually take a lot more to execute the context switching. And if you think about it, it has a lot to do about synchronizing the schedulers on the two processes, the two processors, getting one thread off of one ready queue and putting it in another one. We'll talk about it when we talk about multi-process scheduling. What else do we have? Context switch time increases sharply when with the size of working set. That also should make sense. So if you're dealing with a lot of data and you're using your caches, if you context switch, the overhead of context switching is high because now probably the data that you cached previously has been evicted from the caches, so you have to bring them back to the cache, and that takes a lot of time. So here we're talking about overhead of context switching. So you context switch and you start running your thread, but then the instructions are not executed as fast as they were previously. Let's say you had a memory instruction to load something. So before context switching, when you were, in the middle of your execution, your data was in the cache, you would execute load, it would be really fast. Now you yielded, some other thread came, they used the processor, they evicted your data, and now it's your turn again. Now the cache doesn't contain your data. So it will, now if you execute the same load, this time you're going to go all the way to memory. And if you're not lucky, you might not even find your data in memory. It might be evicted to disk. So your data might need to come from disk to memory and then from memory to caches, so a lot of time. So that would, in some cases, get more than 100x time, which is something to definitely keep in mind. So a little bit more about kernel versus user-managed threads. So this is the one that we have been talking so far. So for each user space thread, we're creating a TCB. We're creating a kernel stack and a TCB inside kernel. This is basically easy to understand. It's convenient to use from the user's point of view. Every time they want to create a thread, they just call a system call. And then the kernel takes care of everything. And then whenever you want to context switch between threads, again, it's done by the operating system. Every time you want to find the new thread to run, the user's space threads don't need to worry about any of that. The kernel would take care of all of it. Context switching, choosing the next thread to run, all of that. And this is basically what is implemented inside Windows, Linux, and Mac, because it's Unix based. So basically all mainstream kernels provide this. And this is basically what you were using in 252 when you were using the pthread create and pthread join and all of that, the pthread library that you were using. So inside the pthread library, basically the library is calling system calls to create all these threads for you. The downside, though, is that this is a little bit expensive. To give you an idea, every time you're yielding, every time you're context switching, every time you're creating a new thread, every time you exit a thread, you're actually calling a system call. And system calls are really expensive compared to just a usual function call that you do inside user space. System calls are extremely expensive. So here you have, in this figure, you have different architectures, Intel, AMD architectures, and then you have just an unoptimized C function call without any parameters. That's the blue line. It takes like 7 nanoseconds, for instance, on Intel. And then you have this get PID, which is a system call. And then you have this get PID system call via VDSO. I'm not going to talk about this one, but this, yeah, just if you're interested in it, go and read. It's out of the scope of this course. So just to mention, these are the system calls that are implemented inside user space. So they're very comparable with just a function call because you're not context switching to kernel. But again, I'm not going to talk much more about that. So just compare the blue bars with the green bars. You can see how much more overhead you pay every time you call a system call. I got a question. So is every thread duplicated in user space and in kernel space? They're not duplicated per se. So in the user space, you have your user stack, which you will use for your function calls, for whatever you use inside your program. You also have your code, your heap. These don't need to be duplicated inside the kernel space. But for each thread inside the kernel, we keep some data structures. We keep a stack associated to that thread. This is a kernel stack that we will use every time we want to context switch, every time an interrupt happens while running that thread. So this is a kernel stack. Again, this is not a duplicate of the user stack. The things that you're going to push on the kernel stack are different from the things that you're going to push on user stack. And then you have the TCB. So you don't need to have a TCB for your thread. So the TCB is kept by the kernel for you, and so on and so forth. So it's not really a duplicate, but you do have to keep some data structure for each thread inside kernel. Okay, I got another question. I thought every system call requires kernel mode. Yes, it does. So this is a special kind of system call. That's why it's taking a lot less code. And you actually cannot implement all sorts of system calls with VDSO. So these are like very specific kinds of system calls that were possible to implement them inside the user space. Again, if you're interested, definitely take a look. But yes, usual system calls, they all have to be implemented inside kernel, which would be basically these green lines, green bars. Okay, so I think I'm going to give you 2 minutes to get up, stretch, and then we'll continue at 2. Okay, we're back. So let's keep going. Now, an alternative to kernel-managed threads is user-managed threads. So in this paradigm, excuse me, you would have the kernel, the user space library to take care of the user threads. So from the kernel's point of view, you only have one TCB for the entire in this paradigm. So you would just, from kernel's point of view, you have one process with one thread. But then the user process will create threads and manage them inside its user space by itself. So nothing prevents you from allocating stack and scheduling your own threads without doing any system call. You can do everything that we just talked about inside user space and manage your own threads. So from kernel's point of view, kernel just looks at you as just one process or one thread. Inside, you could be running any number of threads you want. Now, there are downsides to this paradigm. The fact that from kernel's point of view, all these threads are just one process. The bad thing about it is that if one of those threads blocks on I/O, so if one of those threads call a system call, then the entire process, which could have a lot of threads, would be interrupted, and the control will be taken away from that entire process. Now, you could have other threads inside that would be able to run, but from kernel's point of view, the entire process is now waiting for I/O because kernel doesn't know that there are other threads inside running. So that's one bad thing about it. The second is if you have multi-core system, again, from kernel's point of view, this is just one process with one thread. So why should I give it multiple processors? So other threads inside that process cannot really use multi-core. There are ways to make this a little bit better and friendlier. You could you could use what is called as scheduler activations. So you could ask the kernel to, instead of blocking on I/O, to use non-blocking I/O, and then kernel, whenever the I/O is ready, would send a signal to the user space, and then the user space, the scheduler, would take care of that signal, send it to the thread that called I/O. So this is just a classification of OSS, like mainstream ones. So you could classify them based on how many address spaces they provide, so one or many, and based on the number of threads per address space, one or many. So one address space and one thread per address space. These are the early Macintosh operating systems and Microsoft DOS operating systems. They only had one basically address space and only one thread within that address space. You could have one address space but multiple threads. These are usually embedded systems. This is basically the case with the lab project that you have. You only have one address space, but then you're going to have multitasking and multi-threading. So all the threads are within that one address space. You could have multiple address spaces, but each one of them only has one thread. These are, traditional. These are the early days Unix systems. and then many address spaces and many threads within each address space. That would be basically all the other mainstream operating systems. Got a question, user managed threads, green threads, yes. So somebody asked user managed threads equal green threads, yes. For those of you who know about green threads. Okay. Now, we're now switching to implementing synchronization objects. I believe this is lab 3, I think, either lab 3 or lab 4. So lab 2 is basically what we just talked. It's about creating threads and deleting them. Now, let's talk about implementing synchronization objects. Just to remind ourselves what they are. So inside the hardware, we're going to have a bunch of instructions that we're going to use. So load, store, disabling interrupts, test, and set. And then there are objects that we want to implement. These are mutexes, semaphores, condition variables. And then inside our programs, we can use these objects to implement, let's say, bounded buffers, or producer-consumer locks, or reader-writer locks. So let's implement mutex. And let's just use load and store as primitives to implement them. So first of all, can you actually just use load and stores to implement? Yes. So there's a problem with this slide. I'm gonna fix it on the. Okay, so I'm not gonna actually walk through the code. Hopefully you know about it. This is what you actually implemented into ECE 252. So you can just use basically flags and variables and usual reads and writes to provide a functionality that is similar to mutexes. So here you have two threads, they set a bunch of variables and then they check them. But then this code makes sure that this critical section here, either when thread A is inside this critical section, definitely thread B is not inside the critical section. And when B is inside its critical section, A is not in the critical section. So we have mutual exclusion. Does it work really? Yes, it works, but it's too complex. Even for these two threads, you have to read this code and make sure that it makes sense and it works. The other thing about it is that if you look at the code, they're actually different. So here you make turn 1, here you make turn 0, here inside the while you're checking turn to be 0, here it's 1. So you have different code for each one of these threads. Now this gets even uglier if you have more than 2 threads. For those of you who are interested, you can look at Pedersen's algorithm on how to do a mutual exclusion for multiple threads, just using loads and stores. So again, it works. It's complicated. It's not clean, and it does busy waiting. So here, inside this while loop, we're just executing the same while loop and waiting. So we're wasting CPU cycles by just waiting. So that was take 1. That's the first thing you can do. That wouldn't even require operating system support. A user library can do that, or a user space code can do that. Now the second take, let's implement mutexes using interrupts, by disabling interrupts. If you recall, there are 2 types of context switches, either voluntary or involuntary. So if you think about mutual exclusion, what do you want in a uniprocessor when you're running? All you want is that when I'm running this piece of code, I don't want anybody else to be running this piece of code. Now, if I have a uniprocessor, when I'm running, nobody else is running. All I have to make sure is that I wouldn't get interrupted or I wouldn't lose the CPU when I start running this mutual exclusion code. So that's all I need to make sure. Well, you can make sure that you do not voluntarily yield the processor. So don't call yield inside your critical section. Don't make divide by 0. Don't cause any exceptions. Don't call any system calls. So you would be safe in that context. You wouldn't voluntarily lose the processor. You also can prevent involuntary context switches if you just disable interrupts. So a naive implementation of mutex in a uniprocessor would be like this, something like this. You have a class mutex. It has two functions, lock and unlock. The lock disables interrupts and the unlock enables interrupts. Now, there are definitely problems with this implementation. The first of which is that we cannot let user space programs to use this. Why? Because they could acquire the lock. Sorry, this should actually be mutex lock. They could lock the mutex and then do a while. Sorry, okay. Yep, so this is dangerous. Why? Because here you would disable interrupts, and then this guy is going to do a while loop. And, well, nobody can now take away the processor from this thread. Because interrupts are disabled, even if the timer goes off, it's not going to interrupt this process. So basically, you're screwed, right? So you cannot give this lock implementation to the user program to use. The other bad thing about it is that it doesn't work well in multiprocessors, because when you disable interrupts on one processor, you're not disabling interrupts on other processors. So other processors could potentially run the threads that would access the critical section, and you're compromised. So one way is when you disable interrupts, you send signals to other processors for them to also disable their interrupts, but that's, as you could imagine, is complicated and would require some more work. The third one is that when you disable interrupts, you're disabling something that was put there for a right reason, because you could get interrupts that need to be, you could get events. Events could happen that require immediate attention. And if you disable interrupts and start doing, going to your, even if you eventually enable them, but let's say you have a critical section that is long, you're gonna, go through a bunch of linked lists, and you're gonna do a lot of work. And eventually when you're done, you're gonna enable the interrupts. In the meantime, a lot of things could happen. So even if you have only your kernel threads using it, and all of them are well behaved, even in those cases, disabling interrupts is not something that you really want to do. So let's work on this. It looks promising, but we need to polish this idea of using interrupts. The idea is to use interrupts with a lock variable. So let's look at it. What do I mean? So I'm going to add to the same class that I had, the mutex class, a private variable, and I'm going to call it value, and it's initially free. I'm going to put a queue, a waiting queue, and And then I'm going to provide two public functions, lock and unlock. So the idea is that now for this class, the value and the waiting queue, these two are the shared objects of this mutex. Now this mutex could be used to protect other shared objects, right, inside the program, inside the user program. But for this mutex, this value and this queue are shared objects for all the threads that want to use this this mutex. So how do we implement? Let's start looking at the lock implementation. Let's lock the mutex. We're going to disable interrupts, and at this point we have mutual exclusion. So in a uniprocessor, so this is an implementation again suited for uniprocessors. We're going to check the value. If it is busy, we're going to put ourselves into the waiting queue because somebody else has it. So we will add ourselves to the waiting queue of this mutex. And then we change our state from running to waiting. And then we pick a new thread, and then we switch to that new thread. Clear? Now, at this point, if you got the gist of the lecture so far, you're gonna be put to sleep, and somebody else is gonna start running, right? But at some point, somebody else is going to switch to you, and then when you come back here, we're going to put an invariant that when you come back here, you should have the lock. So you wake up here only if you have the lock. We'll see how this works in the unlock function, but the invariant is that if you wake up and start executing, you get out of this thread switch, now you have the lock. So all you need to do is to change your state to running, because now you're running and you have the lock. And the first thing you're going to do, so let's say before getting out of the if, what is the else? So if the value is not busy, that means that the value is free. Now you make it busy. So you actually locked the mutex. And outside this if and else, the first thing you do after either here or if you go to the else, you enable interrupts. This is the second invariant that we're going to actually make sure in our implementation. Whenever a thread wakes up, the first thing it's going to do after changing its state to running, it's going to enable interrupts. So either you woke up here, you enable interrupts, or you just acquired the lock, well, you disabled the interrupt at the beginning, so here you're going to enable interrupts. Now let's look at the unlock function. How does it look? Again, you're going to disable interrupts. You're going to check the waiting queue. If there is anybody inside the waiting queue, if anybody is waiting for this mutex that you're unlocking, then you can pick one of them. So remove one from that list. Maybe it's first come, first serve. Maybe you have other policies to choose the next one. Maybe you want to put time on whoever has been waiting the most, whatever you have. So you remove one, and what you do is that you now they were waiting, right? So you make them ready. You're not gonna make them running. You make them ready. Now they're ready. You put them to the ready list, and if nobody is waiting, you just make the lock free. You enable interrupts, and you're done. So now this thread has become, the thread that you picked has become ready. So next time they would be picked up and they would start executing. one thing to point here is for those of you who are taking 320 or other computer architecture courses, you know that the architecture, the processor can execute instructions out of order. So when you put disable interrupts, you could also use memory barriers. You could say memory barrier here. They make sure that everything happens, all the instructions before this happen or are committed before executing this, and everything after this will happen after all of these instructions are being committed. So they're here to not only provide mutual exclusion, but also as a memory barrier to make sure that everything has been committed. Okay, I think I'm 1 minute over time, so I'm going to stop here. Let's see what is next. Yeah, we're going to discuss about this implementation and other implementations in the next next lecture on Monday. So with that, I'm going to end the lecture. I will stay inside the meeting for another few minutes. If there are any other questions, I can just answer them in the Q&A. And then after that, I have my office hours if you guys want to participate in that as well. Okay, with that, I will end this lecture. Thank you, and then we'll talk to you again on Monday. Bye-bye.